Hello students, in the last video we have discussed about clipping of line segments, polygons and other primitives. Now we'll see what is nothing but rasterization. As we know, rasterization is nothing but conversion of geometric primitives to a pixel information. And to perform rasterization, we have an algorithm known as DDA algorithm. The expansion of DDA algorithm is digital differential analyzer. Till now we know only the definition of a rasterization, but now we'll see how exactly rasterization can be done using this DDA algorithm. This DDA algorithm is the simplest rasterization algorithm for line segments. Rasterization is also called as scan conversion. So DDA algorithm is the simplest scan conversion algorithm which is available for line segments. In this algorithm we will represent line segment in the form of a differential equation, that is dy by dx equal to m, where m is the slope. Suppose if we have a line segments which is defined by the vertices x1 y1 and x2 y2, then slope m can be calculated as m equal to y2 minus y1 divided by x2 minus x1, where y2 minus y1 can be written as delta y and x2 minus x1 can be written as delta x. So m can be represented as delta y by delta x. In this algorithm we need to have an assumption saying that always the slope value should lie between 0 and 1 and slope value should not exceed 1. Now by considering the vertices of a line segment, that is x1 y1 and x2 y2, we'll try to understand the DDA algorithm. Behind the line segment we are able to observe a grid. We can assume that grid as either a display or as a frame buffer. As we know, on the display and on the frame buffer we have a collection of pixels or an array of pixels. Whatever the smaller rectangles you are observing on a grid are nothing but the pixels. As we know, to display a line segment in a graphics application we will specify only two vertices, and the graphics system will display a line segment between those two vertices. So rasterization is nothing but to display line segment, as a application programmer will give only two vertices and the graphics system will create a line segment between those two vertices. Now using this algorithm we need to understand how a graphics system is going to update all the pixels which are present between those two vertices and how it is going to form a line segment between the two vertices, what we are going to mention. So in this algorithm what we'll do is we'll start from the first vertex, because initially when we give an input to a graphic system to display a line segment we will give only two vertices. So one vertex is identified as x1 y1, the other vertex is identified as x2 y2. But when we execute a program, other than vertices we are able to see the line segment, but we haven't given the line segment as an input, we have given only two vertices. So your graphic system has converted those two vertices to a line segment and it has displayed the output. Now we need to understand how exactly it will display a line segment. For that we need to start from the first vertex x1 y1 of a line segment, and from first vertex we need to move to the second vertex of a line segment, that is x2 y2, and in between we need to update all the pixels in the frame buffer or on the display. Initially the complete frame buffer, that is all the pixels of the frame buffer, will get updated or initialized with the background color. Whatever the background color you have specified, with that color all the pixels will get initialized. Then once you specify two vertices to display a line segment, all the pixels between those two vertices will get updated with a foreground color. Foreground color is nothing but the color which you want to display a line segment. Now to update all the pixels between these two vertices, we will start from the first vertex and will increment x coordinate of each x coordinate each time by 1 unit or by 1 pixel. Initially we will start from first vertex towards the second vertex of a line segment. Each time we will increment x coordinate value by 1. That means we will start at x1 and each time we will increment the value of x1 by 1 until we reach x2. Corresponding to x coordinate value we will increment y coordinate value also. Now in the previous slide we have discussed how to calculate m value, that is the slope value. M value can be calculated as m equal to delta y divided by delta x, which can also be written as delta y equal to m into delta x. As I said, x value will get changed by 1 each time. That means we will increment x coordinate value each time by 1 from x1 to x2. So the change in the x value, that is delta x, will become 1. So we can write that relation as delta y equal to m. Then each time when we increment the x value by 1, corresponding to that we need to increment the y coordinate value also, and y coordinate value is equal to slope value. Because we are incrementing the x coordinate value by 1, change in x coordinate value is an integer value, but change in y coordinate value is not integer value, it is a float value, because slope value, that is m value, is also a floating point value. But when we consider a pixel, pixels are nothing but integer representation. We will say first pixel, second pixel, third pixel, and so on. We will not say 2.5 pixel, 3.5 pixel, etc. So y coordinate value is a floating value. We need to convert it to a integer value first before we represent them as a pixel. So for example, if x coordinate value is 2 and y coordinate value is 3, that means it is the pixel which is present at second row and third column. For example, if x and y value is 2, 3, then the corresponding pixel is the pixel present at second row and third column. So to represent any pixel, the x and y value need to be integer value. So we need to convert the floating value, that is y value, to an integer value. For that we will use a built-in function called round function. Now the pseudocode which is used for this DDA algorithm to update all the pixels between x1, y1 and x2, y2 is we will use a for loop where the x value will start from x1, that is x coordinate or first vertex, ix equal to x1, and until and unless we reach x2. That is why we'll write ix less than or equal to x2. Each time we will increment ix value by 1 or x coordinate value by 1. So we have written ix plus plus. As we increment x coordinate value, corresponding to that we are supposed to increment even a y coordinate value also. How we are going to increment y coordinate value is, each time we will add the slope value, that is m value, to the y coordinate value. So we have written the expression as y plus equal to m, or you can also write it as y equal to y plus m. Plus equal to is a shorthand operator, that is why we have written y plus equal to m. And then depending on the x coordinate value and y coordinate value, which is going to update in a for loop, we will get new pixel between first vertex and second vertex, what we have represented as a line segment, and all the intermediate pixels between two vertices need to get updated with the foreground color. So to update them with a foreground color, we are using a built-in function known as writePixel. This function will take three parameters. First two parameters specify the pixel. The pixel is represented by x comma round of y. Always every pixel in a frame buffer will be identified as x and y, where x represents row number, y represents column number. As I said, if x comma y value is 2, 3, it represents a pixel in second row and third column. So the first two parameters of writePixel says the corresponding pixel, and the line color indicates the foreground color with which the pixel need to be updated. So by using this pseudocode, we can update all the pixels which are present between first vertex and a second vertex with the foreground color. So when we display this, or when we execute this code, all the pixels other than the intermediate pixel between two vertices will get updated with a background color, and all the intermediate pixels between these two vertices will get updated with foreground color. So the result is, here we can observe in a diagram, actually we have specified the two vertices, that is at the two ends of a line segment. Because of this DDA algorithm, all the intermediate vertices between these two line segment will get updated, so they are shaded with a different color, and all other vertices which are not the intermediate pixels are in white color. If we assume that white color is the background color. As I said, here we are using a round function to convert floating y value to an integer y value, because we cannot represent pixel using a floating value. Then, as I said, in this algorithm, always the slope value should be between 0 and 1. Then what happens if the slope value is not less than 1 and when it is greater than 1? In such a case, we need to exchange the roles of y and x. What is the meaning of that is, in the pseudocode what we have discussed till now, each time we are incrementing the x coordinate value by 1 and corresponding to that we are updating the y coordinate value. But whenever the slope value is greater than 1, each time we need to increment the value of y coordinate by 1 and corresponding to that we need to increment the x coordinate value. That is why the algorithm becomes, for each y find the best x.